All right, let's talk about machine learning. So what my plan is, I'm someone that has no experience in this. I'm following a book and I'm gonna work through an example project end to end. And the goal is to illustrate the main steps of a machine learning project. So these are basically the main steps that I'm gonna do. So we need to work with real data. When you are learning about machine learning, it's best to experiment with real world data, not artificial data sets. Fortunately, there are thousands of open data sets to choose from, ranging across all sorts of domains. All right. So what we need to do here is to use the California census data to build a model of housing prices in the state. So we are using the census data, census data, in order to do what? To build a model of housing prices. Build a model of housing prices. All right. Okay, so this data includes metrics such as population, median income, and median housing price for each block group in California. So we have some data metrics. Data metrics including what? Population, income, housing price, etc. All right. So we have block groups are the smallest geographical unit for which the US Census Bureau publishes sample data. Block group typically has a population of 600 to 3,000 people, and we will call them districts for short. All right, so data metrics for districts. So our model should learn from this data and be able to predict the median housing price in any district, given all the other metrics. All right, so we need to look at the bigger picture. So we need to frame the problem. So what is the business objective? We need to build a model. It's probably not the end goal. How does a company expect to use and benefit from this model? So we need to know the objective. So we need to know about the big picture. We need to frame the problem. We need to know what algorithms will be selected and which performance measure we will use to evaluate our model and how much effort will be spent tweaking it. So our model's output will be fed to another machine learning system, and this system will determine whether it's worth investing in a given area. All right. So the next question to ask your boss is what the current solution looks like. The current situation will often give you a reference for performance as well as insights on how to solve the problem. Your boss answers that the district housing prices are currently estimated manually by experts. A team gathers up-to-date information about the district. All right. And this is costly and time-consuming, and their estimates are not great. In cases where they manage to find out the actual median housing price, the median housing price, they often realize that their estimates were off by more than 30%. All right. And what does median housing price means is the middle value in the list of all housing prices in a specific area. And when all the prices are arranged in order from lowest to highest, the median is the price that separates the higher half from the lower half. So it's the middle value. So basically this is just a note. Median. I have median, and we have, for example, the prices in an area are 100K, 150K, 200,000 to 51 million. So what's the middle value? Is if we sort this, the middle value is 200,000. Now the average would be to sum up all of these guys divided by 5, I think we would get around 340,000. But the median value is this one. And the average is much higher because we have this outlier of 1 million, which is a huge outlier. So the company thinks that it would be useful to train a model to predict a district's median housing price, given other data about that district. The census data looks like a great data set to exploit for this purpose. All right, so there is something called pipeline, which is a sequence of data processing components. Sequence of data processing components. And pipelines are common in machine learning systems since what? And pipelines are very common in machine data learning since there's a lot of data to manipulate and many data transformations to apply. Components typically run asynchronously, and each component pulls in a large amount of data it processes. So what I assume, how this goes, we have data, we plug it into a component, it does some calculation, processes it, and it spits it out in another data store. And then I assume this data store, the next component in the pipeline pulls in this data and spits its own output. And each component is self-contained. The interface between components is simply the data store. And this makes the system simple to grasp with the help of a data flow graph. All right, now we can design our system with all this data. So what kind of training supervision the model will need? What kind of supervision will the model need? Is it a supervised, unsupervised, semi-supervised, self-supervised, or a reinforcement learning task? Is it a classification task? Classification task or regression task? Or something else? Should we use batch learning or online learning techniques? Should we use batch learning or online learning? So what are these points? So we have supervised. What kind of training supervision? What kind of training supervision should we use? So we have supervised learning, the model learns from labeled data. We have unsupervised, which the model learns patterns and structure in unlabeled data. We have semi-supervised, where the model learns from a mix of labeled and unlabeled data. Self-supervised, the data itself generates labels. And we have reinforcement, where the model interacts with the world. Then we have classification, the model predicts discrete categories or labels. We have regression, the model predicts continuous values. Clustering, other tasks, anomaly detection. Then we have batch learning, the model is trained on the entire data set in one go. Online learning, the model learns incrementally, and so on and so on. So what's this? So this is clearly a supervised learning task. Why? Because we'll have labeled examples. So it's also gonna use regression task. It's a regression task. It's a typical regression task because we are predicting a value. It's regression task. And it's more specifically a multiple regression problem, since the system will use multiple features to make a prediction. Then we are going to use plain batch learning. because there's no data continuously coming to the stream. And that's it. Now, we need a performance measure. And a typical performance measure for regression problems is it's the root mean square error. Root mean square error, or RMSE for short, and it gives us an idea of how much error the system typically makes in its predictions, with a higher weight given to large errors. And we also have a mathematical formula of it. So what do we have here? We have the formula, which represents the root mean square error, which is used to measure how far off machine learning model predictions are from the actual values. All right, so how does it look, this formula? RMSE, so it's 1 over m. Then I have a sum starting from 1, going all the way to m. X with an exponent of phi minus epsilon with an exponent of phi squared. So this is the formula. I have no idea what it does. So what does it measure? It measures you how much error. All right, so it measures. What does it measure? It measures how far off a machine learning model predictions are from the actual values. So this is the formula. What do we have? What are the components? We have m, and m is the number of examples in the dataset. We have this value here, which is the predicted value for the ith example. For the ith example, we have this, which is the actual value for the ith example. Now this together calculates the error for that example, which is the difference between predicted value and the actual value. Then we need to square the error, which makes all errors positive and emphasizes larger errors. We also need the average of all the squared errors, and we need to take the square root to bring the units back to the original scale, so it's easier to interpret. Okay. The actual price, which is y. If I have a house that costs 200k and another one which costs 300k, then we have the predicted price, which is h of x, which is, let's say, 201k and 300, maybe 290k, and then we have the error, which is 10k here minus 10k there, and then we have the squared error, which is this here. That's 100 mil, because 10k squared is 100 mil. Another one, 100 mil. Now let's plug these values into the formula. So we have 110 plus 110. We have only two elements in our data set, so it's 110. And we need to take a square root of this, so RMSE is on average 10k. So this, which means on average our model's predictions are off by 10,000. So this is useful because it shows how well the model is performing. The smaller the LMSI, the better. It penalizes large errors more, which can be important in tasks where mistakes are costly. All right. Okay, I already said n is the number of instances. X is a vector of all the feature values, excluding the label. And I is the ith instance in the dataset. This is the actual value. So let's talk about our vectors. So if we have the first district in the dataset, which is located at a certain longitude, a certain latitude, a certain amount of inhabitants with an income of a certain amount of money, so we can write something like this. So this is the vector of all the feature values, and I can write, let's say, this is the longitude, this is the latitude, the amount of people, the median income. So this is a vector, and I can also write the median house value, which is, let's say, something like this in US dollars. All right. So X is a matrix containing all of the feature values, excluding the labels of all the instances in the dataset. There is one row per instance, and the ith row is equal to the transpose of X, Y. All right. If the first district is as described, then the matrix X will look as this. All right. Now we have also the big X, which is a matrix that contains all the features from the datasets, excluding the labels. So contains all the features from the dataset, including the labels. And each row in the matrix is one example in the dataset, and each column in the matrix is a feature. All right, so X is a matrix that contains all the features or input data from the dataset, excluding the labels. And each row in the matrix is one example of the dataset, and each column in the matrix is a feature. So if you have m examples and n features, all the features or input data from your dataset, excluding all labels, and each row in the matrix is one example. Each row is one example, and each column is a feature. So X is gonna be a matrix with m rows and n columns. So it's X1. So X of I is the vector of features of the ith example. So H is our system's prediction function. It's also called a hypothesis. When your system is given an instance feature vector, it outputs a predicted value for that instance. So if our system predicts that the median housing price in the first district is 158,000, then the predicted value y hat. So the predicted value is y hat. All right, so in some context, we might prefer to use another function. I don't care about this right now. But this root mean square error is a way to measure the distance between two vectors, the vector of predictions and the vector of target values. Various distance measures or norms are possible. Computing the root of a sum of squares corresponds to the Euclidean norm. All right, so we are using the root mean square error, and it's a way to measure how far off our model's predictions are from the actual values. And they are like distance measures between two sets of numbers. One set is the predicted values, and the other set is the actual target values. So we also have something called a norm, which is a fancy way to describe a measure of distance. And we can have different types of norms. So for example, with parameter I, we have the Euclidean norm, which is the regular distance between 2 points. So it's just the straight line distance between 2 points in space. So we square the differences between each predicted value and the actual value, we add them, and then we take the square root of the result. We also have may or mean absolute error. So this is another type of norm. It's the Manhattan norm. Instead of straight line distance, we are measuring distance by summing the absolute differences. So we take the absolute difference between each predicted value, we add them all up, and we divide by the number of example numbers. And we also have generalized norm. All right. So we can have generalized norm. If we put k is equal to 2, we use Euclidean norm. If k is equal to 1, we use the Manhattan norm, and so on.